concepts of equilibrium. So let's look at dynamic and static equilibrium. The word dynamic by now should already be a familiar word to you. Dynamic means to be moving or to be in motion, while static means to be at rest. Equilibrium means a state of balance. So what do we mean by equilibrium? Dynamic equilibrium. An object is in equilibrium when it is not accelerated, that is, there is no net force acting on it in any direction. So when the body is moving with a constant velocity in a straight line, or when it is rotating with a constant angular velocity about a fixed axis. So we say this body is in dynamic equilibrium, moving with a constant velocity along a straight line or rotating with a constant velocity along a fixed axis. But when the body is at rest, the body is said to be in static equilibrium. So a body is said to be in equilibrium when it remains at rest, that is static equilibrium, or moves in a straight line with constant speed. In this case, we say the body is in dynamic, or if the body is either not rotating at all or is rotating at a constant angular velocity. So when there is motion involved at a constant velocity, we talk about dynamic equilibrium. But when the body is not in motion, we say it is in static equilibrium. So this brings us to resultant and equilibrant forces. What is a resultant force and what is an equilibrant force? So this is the diagram of a resultant and equilibrant force. Don't worry, I'll take you guys to the laboratory and we're looking at the force board experiment. So the resultant force is that single force which, acting alone, will have the same effects in magnitude and direction as two or more forces acting together. The resultant force is that single force which, acting alone, will have the same effect in magnitude and direction as two or more forces acting together. It is found by the parallelogram law of vector addition. By now, you should already know the parallelogram law. The equilibrant of two or more forces is that single force which will balance all the other forces acting together. It is equal in magnitude but opposite in direction to the resultant force. So the equilibrant balances while the resultant is equal when it comes to effects. Take notes. Comparison between resultant and equilibrant forces. So let's look at a comparison to make it more distinct between resultant and equilibrant forces. So, resultant, it is a single force that produces the same effect as that of a system of forces acting on the body. So, that's one. It produces the same effect as that of a system of forces. Could be two, could be three. Secondly, the resultant forces produces accelerated motion of a body. Also, the algebraic sum of forces along with their resultant is not equal to zero. So please take note. Resultant force results in motion, accelerated motion. Then the algebraic sum of forces along with their resultant is not equal to zero. What about equilibrant force? It is a single force that is equal in magnitude but opposite in direction to the resultant force. So it is a single force that is equal in magnitude but opposite in direction to the resultant force. The equilibrant force maintains the static equilibrium of a body. Since it balances, remember it is opposite in direction and it balances the force system. So it helps the body to be in static equilibrium, that is, no motion or in a state of rest. The algebraic sum of forces along with their equilibrant is equal to zero. So I need you to note that. The algebraic sum of forces along with their equilibrant is equal to zero. So if three forces, F1, F2, and F3, acting at a point, are in equilibrium, the resultant of any of the two forces is equal but opposite in direction to the third force. Any one of these forces is said to be the equilibrant of the other two. Also, In this case, the line of action of the three forces keeping a body in equilibrium must all pass through one point. The line of action of the three forces keeping a body in equilibrium must all pass through one point. So I need you to note that. So you can see three forces here acting at the point O. Three forces F1, F2, and F3. So it means any of the third force can be the equilibrant. So let's look at an example. Two forces 10 Newton each are inclined at 120 degrees to each other. Find the single force or the singular force that will A, replace the given system of forces, then B, balance the given system of forces. Of course, you should know that the force that will always replace a given system of forces in effects is the resultant force, while the force that will balance the given system of forces is the equilibrant force. So let's see how to go about that. I told you previously that how to get the resultant force, we use the parallelogram law of vector addition that states that if two forces are represented by the adjacent sides of a parallelogram, then the resultant can be determined the magnitude and direction by the words, by a line drawn from the diagonal of the parallelogram, and is taken in order. So let's see how to go about solving this question using the parallelogram law of vector addition. Remember, the resultant force is a vector that has magnitude and direction, and the equilibrant force is equal and opposite to the resultant force. So the resultant force is given by r squared is equals to 10 squared plus 10 squared plus what? 10 times 10 equals 120. That is, remember the formula, a squared plus b squared plus what? 2ab plus theta plus 2ab plus theta. That is to say, there's supposed to be a 2 here. 2 times 10 times 10 times cos 120. So there's supposed to be a 2. A squared plus b squared plus 2ab cos theta. Because the angle between the two forces, 10 and 10, is 120 degrees. So it's a squared plus b squared plus 2ab cos theta, where the theta in this case is 120 degrees. So that is so remember, cos 120 is equals to minus cos 60. Cos 120 is equals to minus cos 60. So the equilibrant force is when you take the square root of 100, you will get 10. The equilibrant force is simply 10 and is equal and opposite to the resultant force. So let's look at equilibrium of three forces acting at a point, triangle of forces. The three forces that keep a body in equilibrium can be represented in magnitude and direction by the three sides of a triangle as shown below. So here is a figure. You can see that when two forces now, together with their resultant arrow and the equilibrant E, are acting at a point, they can be represented by the three sides of a triangle. So taking in magnitude and direction, of course, so taken in order. So that's the concept or the idea behind the triangle law of forces. The triangle law of forces. So here are we can look at this picture and get a better understanding of what we are talking about. So what do we mean now? Let's look at the analysis of the diagram. The analysis of the diagram. So here is the initial diagram that was given. OB represents the force Q in magnitude and direction. OA represents the force P both in magnitude and direction, and CO represents the equilibrant E in magnitude and direction. The triangle shown below is the vector representation of the three forces acting at O. That is to say, you can take any of the triangle what? OCA or triangle what? OQC. So, because a triangle has three sides, so you have triangle OQC, or triangle OCA. So when you look at it, we can resolve any of the forces together with the words, with the resultant with the three sides of a triangle. So what is now the idea behind the triangle law of forces? The triangle law, thank you. So you can see this is the equilibrants or the resultants, and these are the two other forces now, force P and Q. Forces P and Q acting together with the equilibrants to form what? A triangle. So the principle of triangle of forces states that if three forces are in equilibrium, they can be represented in both magnitude and direction by the three sides of a triangle taken in order. So any three forces, now the idea is that these three forces must be coplanar. That is to say, they must be acting at a particular plane or at the same plane, and also the other condition is that their line of action must pass through the same point. That is to say, the line of action of the three forces must pass through the same point. The three forces must also be coplanar for we to use the principle of the triangle of forces to resolve this three force into direction.